All right, we're very happy to have Andreas Blommaert, who will tell us about gravity factorization.
Okay, hi guys and well, girls. Thanks so much to the organization for having me today. I'll talk about some work from last winter with Luca and Jorrit, and I'll also add in some new stuff based partially on discussions with Christian, one of my friends in CISA. This is the program for today. I think the first 5 segments will be like 2/3 of the talk. That'll be about this paper in November. But I think maybe some of you already saw a talk by Jorrit or Luca. And to account for that, I also included some new stuff so that like everyone maybe finds something interesting out of this. That'll be the last third of the talk. Okay, so for a little introduction. Yeah, as you all know, sort of the topic of this conference, understanding the duality between black holes and quantum systems is a huge open problem in quantum gravity, of which we understand several things. And there's been much recent progress over the last couple of years, in particular, I would say by studying wormhole amplitudes or wormhole contributions in various forms and shapes. However, this existence of wormholes has also introduced new puzzles, and I'd like to address one of those puzzles today to the degree that it's possible. And that puzzle is a factorization problem, which is saying that because there's wormholes in gravity, when we compute, say, the square of 2 partition functions, or the square of a partition function, it will not be like the square of the thing you compute for 1 partition function, because there's wormholes that can connect the 2 asymptotic boundaries. And this is in tension with, well, quantum mechanics, and it directly implies a statistical interpretation of our gravity theory, or at least when we try to write the gravity theory in a holographic context, it applies that it is dual to some sort of ensemble. And so what this means is that unless there's some sort of a magical cancellation happening, that will always have this problem. And therefore all simple models of gravity, be like Einstein-Hilbert gravity in whatever dimension you prefer, or supergravity, they will all be dual to ensembles. Though we of course can't write up the specific thing, but it's obvious that there's statistics because the variance is non-zero. A second problem, which is kind of related, and solving one kind of solves the other, is discreteness. Saying that the dual in ADS-CFT has a discrete spectrum, but the examples that we know of simple models of quantum gravity, like, well, certainly JT gravity and probably also Einstein-Hilbert gravity in 3D, have a continuous spectrum. And this tension you can see sort of experimentally. For instance, when you look at the late time 2-point function, it'll have like these erratic oscillations, or maybe more importantly, if you compute the matrix elements of Hawking radiation, it will look something like this, and it's sort of erratic also. And this sort of this fine print that makes these things deviate from a nice smooth curve is something that simple gravity doesn't really know about. It doesn't know about microstructure, and it doesn't know about the spectrum of black hole microstates. So, okay, how do we proceed with this? What will be the idea of the talk? So we, being I guess me, Luca, and Jorrit, we believe that UV complete theories of quantum gravity, they should factorize, they should have one discrete spectrum. Like in a nutshell, they should just be like standard examples of ADS-CFT. Of course, it's well, not super obvious, but we believe that should be the case. And then the question becomes, what is the fundamental difference between such theories, UV complete theories, and these simple models of gravity. So are there any sort of effective ingredients that we forget or we forgot in our simple models that we can add to the theory to sort of understand in a, well, in a tangible way how this problem is resolved in UV complete theories? What we claim is that the missing extra ingredients are tiny, like super tiny, because there's an e⁻²⁻² black hole entropy multiplying the coefficient. Tiny non-local interactions in the gravity theory. For instance, in Dilton gravity, we can have this bilocal potential. And furthermore, we can also consider local deformations in Dilton gravity, as we've become accustomed to. And the idea is a bit that those could, for instance, arise by integrating out matter determinants. For instance, the matter loops that Jeffers and Kolkmeier and Sonner and Bauer are considering, they would give rise to these types of bilocal interactions. So the idea is a little bit that integrating out matter could give rise to these terms and could explain factorization. Sorry? Yeah, the question was, this would not give rise to interactions between separate spacetimes, because the matter determinants will live on individual spacetimes. Though I think the sort of picture I want to portray is that we do have all the geometries in the theory. So when I compute the partition function with two asymptotic boundaries, I do allow for connected contributions. I do allow for wormholes, but I also allow for something like matter on those wormholes. And then if you integrate out the matter, you would also get interactions between the two asymptotic boundaries, if that makes sense. I'm not sure if that was very convincing, but regardless of this matter interpretation, we can.
Sorry. Yeah. So I think, if I understand correctly, then you will use this non-local interaction to provide an interaction between two different spacetimes, right?
Right.
So, if I understand correctly. So I think if you motivate it by saying you integrate out matter fields, it's not very convincing.
Okay, that could be true. Yeah, well, this is, I guess, one idea. Maybe it's not the correct idea. Maybe, but I guess the main point I want to make is that you need those non-local interactions, and then we can figure out where they should come from. But I think the point is legit. So the claim that we had is that there should be a universal formula for this bilocal interaction, at least in 2D gravity theories. A bilocal interaction that you should add that makes the Dilton gravity theories factorized. And this guy looks a little bit daunting, perhaps, but it's decomposed into components that I'll explain to you what they mean. But the more physical way, I think, of thinking about it is just do the B integrals, and you get some sort of potential that depends on phi at one location and phi at another location that is symmetric in those two locations. And that would be like, I guess, standard non-local interaction you could add to your theory. Okay, the local potential I will decompose in sort of a similar basis, and I'll explain to you what that basis means. Now, before I prove why this works, I want to first comment on the implications. Then maybe you can tune out for the actual computations if you want to. And I guess the major implication is that we need to include non-local interactions in low energy effective field theories in order to cancel contributions from wormholes and avoid a factorization problem. Maybe you don't want to avoid that problem, but if you do, then I think this is what you need to do. The non-local interactions are tiny, and so they won't really affect your sort of everyday observables. If I do an experiment here, I won't see effects of this stuff, of course. They're enormously suppressed.
I mean, isn't this the same as saying that you just forbid wormholes?
That you just
forbid wormholes?
I don't think so, because what we do is we have all the geometries and then we add interactions on top of that. And then, okay, if you start computing the numbers, then the numbers can cancel, but I don't think that's the same as a priori putting in like ad hoc that you don't have the stuff. It's more of as a consequence that.
Well, but you didn't derive independently this blue little diagram. I mean, this blue diagram comes because it was designed to cancel the other diagram.
Yes.
So, of course, in a theory that has some diagrams I don't like, you can just add a gauge field that cancels precisely that diagram, and that's equivalent to not including that diagram.
Right. Well, I think to me the thing that sort of makes it non-trivial is that you can just view it as sort of a bilocal term in the action. It's not that we're just putting in those diagrams. Well, in the end, we'll end up having those diagrams and canceling other stuff. But I think the non-trivial thing is that we start from just a theory on all geometries with some interaction patterns. And it was not, at least to me, maybe it's obvious to you, but it was not to me obvious that by tuning non-local interactions of this dilaton field on these geometries, that you could cancel the entire sum over geometries. That was, well, to me, not obvious, and that's what I want to tell you today.
Well, in this theory, the wormholes themselves are some induced. You can view them as induced in a non-local interaction. So
yes.
It's not surprising that if you add minus that contribution.
Yeah, that's true. Okay. Now the second point is that the details of the binary coupling constants, or the J, IJKL, and SYK, or the Hamiltonian, it's kind of the microstructure of the theory. They translate to details of the local bulk couplings. So this local potential that we have encodes sort of the full microstructure of our theory, if you want. And in that sense, you can interpret the simple JT gravity as an ensemble of more quote-unquote realistic gravity theories.
Here I have the same comment as before. You're adding the answer you want and you're subtracting the answer you had.
I'm what?
Could we go back to the previous transparency?
Yes.
So the last line, it's saying that
right.
You add the answer you want and you subtract the answer you had.
Yeah, I guess in this case it's a bit stupid, but you can have a bit more non-trivial of these Z-brain guys, which don't look like they're just subtracting something. And even in more generality, we discussed this in the other paper about alpha states in February or March. It's sort of the potential can take a sort of generic form, and still the details of the potential will end up determining the spectrum of the theory. In this case, it looks a bit manufactured, and it is, of course. We designed it to work, and it looks stupid, but it's a more general statement than this.
It might be the right answer in this case, where you supply the Hamiltonian by hand somehow, because that's the rule of the game, right?
Yeah, I think
some other systems you maybe supply by hand some local construction of the Hamiltonian, and then the energy levels you compute by solving that.
Yeah, that would be more a bulk first computation, I guess. This is more in the spirit of you give me a boundary system, and you force me to give you a bulk theory that reproduces the answers, and then I think this rolls out. But I guess what you would really like from a, or prefer from a gravity point of view is you have some bunch of interactions and, like you say, energy levels roll out rather than the other way around. But,
right. I mean, here you have the philosophy. You say, well, you supply Hamiltonian.
Yes.
In usually in many body systems, we don't supply but we give the Hamiltonian, but the Hamiltonian is not given in terms of the energy levels of the many body system, but in terms of some local interaction, some elementary field. So we have some description of Hamiltonian in terms of some simple operators, and then we have to figure out how to find the energy levels. The energy levels is the answer to some questions about. It's not the input, the data. I mean, in this case, you have the energy levels of the input, and that might be fine. That's what you are doing in this case. I think I'm not sure what the roots of the game should be. I'm just contrasting, let's say, two possible things. Like when
it's not clear to me how to proceed if you would just give me like, oh, this is the boundary Hamiltonian with this sort of interactions. I'm not allowed to calculate the energies. Then how to guess the dual bulk picture on the nose? I don't know that. Maybe there may be a way to do that. That would be cool. Yeah, indeed, we picked the rules of the game here to be give me a Hamiltonian. Let's see what goes on in the bulk. It's not maybe a complete solution, but it's something, I think. Okay, so the last comment on this slide was that the local interactions, they are tiny too, and which I think they need to be, because the simple theories of gravity, as we all know, are often a very good approximation. Like a lot of things can be computed even with just classical gravity saddle points, and those should still be valid. The tiny local and non-local interactions that we include here, they only become important when we ask kind of extreme questions, like we wait for super long times, or we probe in or near black hole interiors. And then you should see the fine print coming out. I think this raises a question, namely, suppose we have these non-local interactions in our low energy effective field theory or our gravity description, then what played the role of these things in the original UV-complete string theory? And we thought of a picture like this, that should make sense. That if we take some string theory, then clearly the string path integral will include like all possible types of metric fluctuations. So in particular, it should include configurations that look like quote unquote classical wormholes, whatever that means. I don't know how to build those configurations in string theory, and that seems to be it seems like an important open question to me. But supposing that you can make them, then you should also find, if you're super powerful, that there are other configurations in the string path integral where two spacetimes get sort of connected, but in a way that the connection is like very stringy or something. It looks nothing like classical geometry, like a bunch of other stuff can be excited. And like somehow these should cancel the geometric contributions that we have a nice picture for. And I would say that sort of this, maybe we can think of the blue mess as sort of a tiny wormholes or something. And those tiny crappy wormholes would be something that we would be more keen to integrating out instead of the large sensible wormholes or semi-classical wormholes. And then the tiny crappy wormholes would give the non-local interactions in our gravity descriptions, whereas the usual wormholes we kind of like to keep around because we have a nice picture for them. And a picture that we can, I guess, experience also as low energy observers. Okay, of course, I don't have anything concrete to say here. It would be super cool if someone could work even out how to build a wormhole in string theory. I haven't seen that done. Okay, now for a couple of formulas. I just want to prove this claim that the theory I introduced on slide 7, that theory is going to factorize. Okay, so we have this JT action with a deformation. And the ideas, because I want to advocate the cancellation of Feynman diagrams, I do the same thing I always do in quantum field theory. I expand out the interactions. Okay, so we do that here. Okay, the left-hand side should be e to the minus I deformation. And I expand out the exponential and I get all these terms with different interaction vertices. And the OGs you should view as interaction vertices in this picture. The expansion coefficients, which we call Z brains, are the numbers that I put in my, my action. And then we have sort of these interaction vertices or basis deformations of the action, which are these cosines. So they're sort of the Fourier modes in some sense of the dilaton. And to prove this cancellation of Feynman diagrams, the key is that these OG guys, they have an interpretation as geodesic boundaries of length B that we insert in the JT path integral. So there's various ways to appreciate this, but I think most intuitive is to use a story that I think people are more familiar with, which are the defects in JT gravity. So they correspond with a e to the minus 2 pi minus alpha phi operator that you insert in a path integral, and this creates well, a conical deficit. You can analytically continue this on both sides of the equation and get a geodesic boundary. This is sort of it's known that this works for hyperbolic geometry. So you go from e to the 2 pi minus alpha to e to the 2 pi times cosine, because you can take both the branches. And now the deformations on this previous slide where I had these operators inserted with these wave functions. So it means what we have is we have a boundary, a geodesic boundary, and we integrate that with some wave function psi of b. And we color that boundary blue because, well, we like using multiple colors, I guess. But the important point is that we also get contributions like on the last line here, where there's like a wave function that connects the two boundaries. And that comes inherently from the non-local interaction. So in the paper, we called this a correlated brains, because they're brains because we have an exponential of boundaries, and they're correlated because the boundaries can be correlated like this. And yeah, I want to point out that this is very similar to what the Steve Schenker, Saad, and Yao did, where they introduced correlated boundary components. But I think the extra step, or the key extra step, is that we have an exponential of these boundaries. And the exponential is necessary to allow the theory to factorize to all orders in the genus expansion, and not just in the leading order approximation. And this exponential, as I pointed out, you get naturally from putting things into action. Okay, so our deformed theories look sort of messy if we draw them out in Feynman diagrams. We can have all the wormholes, and then all sorts of non-local interactions on the surfaces. Fortunately, there's a nice way to organize these sums, as I'll show you shortly. Okay, so if you remember the claim, we said that with specific values for the coupling constants in the action, in principle, we could also allow for trilocal and quadrilocal interactions, etc. These are depicted by the Z brains with multiple entries. But those guys, you can prove you all need to put to 0. So with these interactions, we can prove that the theory factorizes and has a discrete spectrum, and that the computation of each partition function after you do the computation collapses to only 2 geometries. Yeah, I guess one comment that you could have, which you had, and we also heard previously, is that you can say, well, you just choose to not have the wormholes. Well, this is not how I think about that. As I told you, I think the wormholes are still around, but we add these interactions on all geometries, and then everything cancels. But maybe it's a bit potato. I'm not sure. At any rate, all the geometries cancel, and only the disk and what the guys called half wormhole remains. So I want to show you how we can make this work to all orders in the genus expansion. Furthermore, you can also work this out non-perturbatively in the matrix integral formalism, but I will spare you of that today unless you have some extra time. So I think it's pretty fun, but well, let's keep it short. So the first thing we want to check is that this last equation is true, that this finite trace can be written as a sum of two geometries. And this is just an exercise in Gaussian integrals. In particular, if we want to compute this bottom amplitude here, we have this trumpet and then a wave function we put on the trumpet. Now this B integral we can just do, and it gives you a e to the minus beta energy. And you get the correct sum out of that. That's sort of the gist of that, which of course we designed it to do. So it's sort of. Now for the more important piece, I think, which is the factorization argument. So we want to prove that this bilocal deformation has the effect of canceling all wormholes. And the workhorse formula here is the basic formula that already also appeared in the paper by Shankar and company, which is that the sum of these two guys is 0, because if I take z brain to be minus this delta function, then this gluing integral is precisely the same as what you do to compute the wormhole, except for the minus sign. So that's kind of stupid, but the fun part is how this works to all orders, which I think is, well, to me is the main argument of the paper. Namely, we have this complicated sum over geometries, then we can group the geometries together in such a way that there's amplitudes on these circles that are very close to the boundary with or without a brain two-point function. And if you think about it a bit more carefully, you see that there's essentially 4 options in case we have 2 boundaries. Namely, I pick one super complicated bulk amplitude, can have whatever. And then at the boundaries, I choose to either yes or no include this brain two-point function. And now I sum up all these guys, and I sum over all sigma, and that should compute for me the complete connected correlator. And the point is that for any sigma, the sum is 0. In particular, if I do this integral of this amplitude, I get the first amplitude, but with an overall minus sign. And the reason is that if you compute these amplitudes, in general, it's hard to compute these amplitudes because there's something called the mapping class group, which makes computation of JT amplitudes a bit more difficult. But the mapping class group is super simple, close to boundaries, which means that close to boundaries, you do have a notion of gluing things on and off, whereas you cannot take like a genus 5 Riemann surface, cut it in half, compute the amplitudes and glue them together. That gives the wrong answer. But near the boundaries, it does work. So what you get here is a minus sign for this amplitude, a minus sign for the top amplitude on the right. And the one on the bottom gives -1 squared. So you have 1, -1, -1 plus 1 is 0. Super complicated. And so the full connected correlator is going to vanish. Okay, so this argument extends almost obviously to any number of binary components. So for any, again, super complicated sigma or super simple sigma, whatever I want, I have m boundaries and I can choose to either yes or no have a brain there. And this choice, of course, I want to emphasize again, to have that choice, it's important that you had an exponential of these insertions so that you literally sum over all options. But now when we start computing these amplitudes, each of these give each of the amplitudes on the left gives the same answer as the amplitude on the right, up to a minus sign to some power. And we can just sum the minus signs and they give 0. But in fact, you don't even need this sort of binomial expansion. You can also just look locally at one boundary. I can add this guy with a guy with the same number of brains on the other boundaries, but with no brain here. And those guys already cancel. Okay, this argument is also valid when we have one boundary. And again, all the amplitudes would cancel. So I think this sort of proves my statement that in this theory where we add the bilocal dilaton interaction and local dilaton interaction, once we go through the math and actually compute the Feynman diagrams, we find that there's a massive cancellation between the Feynman diagrams, and only basically 2 diagrams remain, which is the disk and the half-Hermel. And they compute the partition function of a discrete theory that factorizes. Okay, this concludes the JT part of the story. Now I want to tell you about sort of an application of this idea to a different theory, which I think also works. And namely, we'll focus on 3-dimensional gravity this time. In this setup, I'm not particularly interested in the fact that we can make the theory factorized because, well, we already solved that problem in JT. But I think it's a byproduct of this factorization that I think is sort of interesting, or fun at least. So yeah, the following is going to be work in progress, a bit more schematic, and based partially on discussions with Christian. So remember that in ADS-free gravity, suppose we compute the partition function, then we, okay, I also only discussed torus boundaries today, by the way. So we can compute a partition function by summing over all 3 manifolds that end on a torus, in principle. But there's a million problems with this sum. The first is that we don't even know how to classify to the degree that, well, to the best of my knowledge, we don't know how to classify those manifolds. The second is that the individual amplitudes would diverge. For instance, if we take manifolds that are sigma, well, that are genus Riemann surface with one boundary times a circle, such that the boundary is this torus and everything just has this U1 symmetry, then all the amplitudes are infinite. And okay, there's ways to prove that via canonical quantization. And then the third problem is that even if the amplitudes were finite, there can be divergences coming from summing over subsectors in M. For instance, if the sum over genus in genus G Riemann surfaces times S1 is probably asymptotic. And it certainly is in the case of chiral gravity, which Lawrence Eberhard discussed recently. In that case, he found a way to compute these amplitudes explicitly. And well, the sum over genus is, well, it contains as a limit the JT sum over genus, which is already asymptotic. So this sum is asymptotic too. And in the chiral gravity case, the amplitudes are actually finite. So it's an extra problem on top of the ones that we already have. Okay, now this pure 3D gravity, we should think of as sort of similar to JT. Like it doesn't factorize and it's no discrete spectrum, presumably. But I want to sort of construct what I think is a sensible class of deformations of 3D gravity, which do factorize. And I want to explain how to construct those. But I think more importantly, I want to show that those don't suffer from any of the problems above. Basically, from the same reason, for the same reason as in JT, that there'll be Feynman diagrams canceling for all three manifolds except for super simple ones, and you get like a very simple answer. Again, this is not like something that you derive from the bulk, but the game I want to play here again is, suppose that you made a major breakthrough and you found a 2D CFT which has a vacuum and then a bunch of discrete spectrum of black hole states with certain spins. That would be amazing. I don't know how to do that, but the question I want to ask is, if you give me if such a theory is found, is there a bulk dual that is close to just regular gravity? And I think that is something you can probably do. So what I want to argue is that you can construct deformations of 3D gravity where we just end up with this finite discrete sum, which is sort of pictorial, but if you want to write it in CFT formulas, the first is like chi0 squared, and the second is like chi h bar or something, where h and h bar are the weights of the left and right moving weights, and chi are Virasoro characters. Now, of course, I'm overselling a little bit. I'll only talk about this chiral gravity that Lawrence discussed today. I think it should also work for the full 3D gravity, but there's still some problems with the Kotler-Jensen's measure that we haven't been able to solve yet. So it's not a full thing, but the aforementioned problems also exist there. So I think it's still a good toy model. In principle, like there's still a sum over all three manifolds, and there's still divergences in the individual sums over them. So now I want to consider the following deformation of the action. I don't have the best motivation in the world for it, except that it's designed to work. So let's go with that and then try to figure out what the motivation is. So I want to insert basically an exponential of correlated Wilson lines, where, okay, these WNs are Wilson lines of SL2R times SL2R with a certain energy and spin, appropriate units, and along some curve C, and we allow all curves C just like we allow all positions for the local operators to be inserted. So the Wilson lines are a bit like single particle path integrals in ADS3. So I'm thinking of this as, again, roughly related with integrating out matter fields, because well, a matter partition function is like an exponential of lines. So it's closely related with these exponentials of Wilson lines. But okay, let's not dive into that too much, perhaps. Now, the basic reason why this theory, this chiral gravity theory, is manageable is because we have this equality here. And you should think of that as similar to in dilaton gravity, where we have the relation that any amplitude can be decomposed in a trumpet and a Wald-Petersen volume. Here it's more like it's like these statements in Chern-Simons theory that an amplitude of Chern-Simons with a torus boundary has a decomposition in characters. And there's expansion coefficients for the characters which you compute like this. Okay, let's be a bit more concrete about this though. The blue line is representing one of these Wilson lines. And so this first torus in a chiral gravity context computes one Virasoro character with a certain energy and spin, which is discretized because it needs to be T invariant. And M is some generic manifold where you can have any number of Wilson lines inserted, and it can be super complicated. But I want to explain why this equation is true in gravity, not just in Chern-Simons. Basically, I think let's consider first the case where again the manifold is a genus G Riemann surface with a torus boundary and a U1 symmetry, where we can have Wilson lines running along the S1. Then we have this decomposition for the amplitude that Lawrence wrote up. It looks a bit daunting, but it's really quite intuitive. This guy is just a sort of mathematical way to tell you that you're computing the amplitudes of a manifold with the S1 symmetry with Wilson lines inserted along the S1. And these guys, they're like saying, okay, you have this phase space that you need to quantize, and there's a certain symplectic structure on that, and that determines the representations of the Wilson lines that are inserted, or the other way around, like the Wilson lines determine that stuff. But okay, this is not very important for today. The main point is that you do have this decomposition that I show here, and that Lawrence proved that in that case. So as I said, you can view this formula as the application of the formula for Wilson lines in 3D Chern-Simons, but then to chiral gravity. No, the rest is not too important. But the key feature again is that any amplitudes will decompose, or at least those amplitudes with sigma g times s1 will decompose like this in a universal way. And the reason is again simple, namely that the phase space, and okay, these amplitudes in gravity are computed by quantizing phase space basically. But the phase space is just the thing that you're integrating over in the JT path integral. So it's a space of Riemann surfaces with punctures. And there again, you have this property that the difficulty is really dealing with the mapping class group, but because that again acts simple near the boundary, this quantization will also be simple near boundaries, and you'll still have like this decomposition property. And in particular, the sum over n just comes from basically quantizing this BD tau gluing measure in JT gravity. So in particular, because the tau is periodic, this is basically a particle in a circle, and that quantizes the momentum b squared. So you get this discrete set of Wilson lines, or discrete set of lengths, if you want. Okay, so again, to emphasize, this is a standard story of a more Seiberg, Elliser, and Schwimmer. For example, for the analysts, you have this property that they derive. Now, in Chern-Simons, this decomposition also holds for manifolds, 3 manifolds M that don't have the U1 symmetry. And I think the same should therefore hold for gravity. So I think with this decomposition, our back pocket, we can start applying basically the same identities that we had before. For instance, we can cancel the wormhole by this bilocal interaction that we get from expanding out our action. And more generally, we can do that for all the 3 manifolds, where this guy can now have any number of Wilson lines braiding with each other and manifold,
Could you repeat your point about the phase space simplifying? I don't see why that would imply that, I don't see why that simplifying implies that the Hilbert space sort of.
Sorry, I'm not understanding.
In your point that you made about the phase space simplifying near the boundaries?
Yes.
I don't directly see why that implies that the Hilbert space factorizes.
Well, okay, probably because I didn't explain it well. Well, I don't really want to go into details because it's a bit technical, but it's really, you can read the paper of Moore, Seiberg, Elliser, Schwimmer, and it's explained quite nicely there in the Chern-Simons formulation. You do some filter definitions, and then what you end up with is a certain integral, like near boundaries, you have a certain integral over a coadjuvant orbit which in this case will be these b squared and tau coordinates. And then you have some other terms in the action, but they like sort of decouple. You do that, but then you do that quantization of b squared and tau, and they give like terms that you insert then in both terms of the action. Sorry, not explaining it well, but I can assure you they explained it well. Sorry. But there's like, it's well established how to do this. Yeah, I think that's it. I didn't want to formulate it like that because in gravity it's sort of subtle. Like to describe the Hilbert space on a torus, at least when I looked at it. But that's certainly one way to look at it in the Chern-Simons formulation. Like that's a statement that the Hilbert space of Chern-Simons on a torus can sort of be generated by inserting one Wilson line in the bulk of the torus and evolving to the boundary. And each of those guys, if you put like boundary conditions on them, will give like a conformal block, which is a torus character in this case. And that's indeed this like sort of radial quantization or something if you want. Yeah, thanks for that comment. Okay, that sort of concludes my discussion about this. Like all manifolds will cancel, and we end up with this discrete sum, which like is, of course, again, is something that you need to sort of give me beforehand. You need to give me a finite CFT with the properties, and then you can write the bulk theory for it. Okay. Now, a last slide, I think, about the generalization, which we haven't figured out yet. So the canonical quantization for like the actual 3D gravity is quite similar. I think Gottland and Jensen worked this out in part, and Eberhard also. And basically, the sum over n gets replaced by a sum over spin and an integral over energies. And the reason that you have one sum and one integral is basically you have now two of these tau winding things, and one will be compact of these twists. One will be compact and the other will not. So one direction will quantize. One direction will be quantized and the other will be continuous modes. And this is just, of course, again enforcing sort of the T invariance of the boundary theory. So yeah, maybe one would want to consider something like this, where you add like again a bilocal of Wilson lines, but now there's a little bit of a problem. Well, maybe a big problem, because there's extra measure factors on the phase space integral that Kotler and Jensen discussed, and this complicates the above story, and yeah, still remains an open problem, but sort of sympathetic that there should be a way to solve it in similar fashion. Okay, that's it. So a quick recap: factorization demands non-local interactions in our low energy field theory. I really think that's the only way you can get a theory to factorize. The local coupling constants determine the microstructure of the theory, which of course is not very surprising. It's pretty obvious if I give you a theory with different coupling constants that I'll describe a different boundary theory also. Okay, and that the non-local interactions enormously simplify the computations of all amplitudes because there's massive cancellations. Yeah, thanks. That's all.
There are further questions for Andreas? Okay, no further questions. We have
Yeah,
bunch.
we had plenty of questions during
Yeah.
the talk also. So.
And let's thank Andreas again.
Thank you.